background of A and B. A and B, the background color looks different, but when I move the background color to B, again, A color to B is exactly the same, but our naked eyes, it looks different. Okay, again, and the red color, there are two types of red color. Left bottom red color and right upper red color looks different, but when I compare these two colors, it's exactly the same, but it looks different. Okay, our human eyes is very good, very efficient for classification, but our human eyes, our eyes is distorted. We call it its illusion. So it's affected by environment and lights. So we can, we couldn't, discriminate the color efficiently. So there is a limitation of our human colors. So for objective instead of subjective and quantitative measurement, we need a machine and also image analysis. Human eyes, very good for classification, but limited to quantitative analysis. For example, when we look at the red color, how red it is, we cannot quantify with our human eyes. So we need a machine vision and image analysis tool. Okay, and very simple very simple images, color images. This is the color image is also spectral image because it has spectral information, but just the three spectral information: red, green, and blue. This is color images. Using these three wavebands, we can make color images. It's a very simple images. Okay, when we compare color images with hyperspectral images, I want to introduce hyperspectral images. Hyperspectral images has lots of wavebands. Instead of three wavebands, hyperspectral images has sometimes 100, sometimes 1,000 spectral images. We call it 3D hypercube because there is 3D information, X and Y and Z direction. Z direction is spectral information. Okay, so these hyperspectral images, when we look at one pixel, this G direction is like a spectrum. Okay? Spectrum. A spectrum is like different intensity at the specific wavelengths, right? So one pixel is become spectrum in the hyperspectral images. Okay, I want to introduce another terminology, multispectral images. Okay, there are two comprehensive spectral images. One is hyperspectral images, and another one is multispectral images. Hyperspectral images, the wavebands information is continuous, and also the number of wavebands is a lot. But multispectral images, the spectral image is the number of spectral images is less than hyperspectral images, and also the spectral information is discrete, not continuous. There is a difference between hyperspectral and multispectral images. Okay, spectral images mostly use light information. Light, in other words, electromagnetic wave. So electromagnetic wave, there are huge wave range. Okay, when we think about visible range, there's a very small region here. The wavelength is about from 350 to 740 nanometer. That range, we can see the color. That is a visible range. Above the visible range, there is infrared range. Okay, there is a near infrared, short wave infrared, mid wave infrared, and long wave infrared. Those are infrared region. Above the infrared region, there is microwave, terahertz region, and microwave region, and also radio wave region. Okay, there is a shorter wavelengths than visible range, ultraviolet range, and also shorter than ultraviolet violet range. We call it X-ray, and the shorter wavelengths, gamma ray. Okay, so those are overview of electromagnetic waves. In our application, mostly we are using visible range and infrared range because infrared range is very related with the chemical composition of materials. Okay, spectral imaging or spectral measurement, those are interaction between light and material. When light comes in, most of the light reflected, and some of them observed, and very little amount of light can penetrate through the material. So reflectance, absorption, and transmission, and some of them scattered and comes out from the materials after scattering, and some light, there is photoluminescence like fluorescence, if there is a fluorescence material inside the material. Using those interactions, we can collect the spectrum from the material. Okay, spectral information is, we can call another terminology, vibrational spectral information. Why? Because every molecule has a vibration. Okay, each vibration has a frequency. If there is a high frequency, the vibration is very fast. The low frequency, the vibration is slow. Okay, the frequency information is inverse information of wavelengths. So this is an example of one molecule, it's caffeine molecule. Some vibration here, there is some, certain frequencies. In other words, certain wavelengths. This vibration is related to this wavelengths, and this twisting vibration related to this wavelengths, and this stretching vibration related to this wavelengths. So when we look at the spectrum from a sample or material, we can estimate the chemical composition, chemical information of the material. So that is why we call vibrational spectral information, for spectral information. Okay, there is certain functional bands, because each functional structure has its own vibration information, right? So vibration has frequencies, so it's related to wavelengths. Okay, for example, H2O is water, right? When we look at the absorption by water, the absorptions occur at a certain wavelengths, like 740 nanometer and 970 nanometer and 1450 nanometer and the 1950 nanometers. Okay. Usually, food and agricultural material, the main molecule or main atom is C, carbon, H, hydrogen, O, oxygen, and N, nitrogen. Okay, so those combination, make molecular and agricultural materials. So here there are lots of combinations, CH and some NH. Okay, there are those combination has its own unique frequency or wavelengths. So which where the light absorption occur. Okay, again, there are several functional groups related to certain wavelengths or frequencies. So you can refer, this information, for analyze your sample using spectral information. Okay, let's move on spectral images. Why spectral imaging is necessary? Okay, when we look at these figures, when we look at the spectrum, mostly it's a point information, point measurement. When light, illuminated, and we just get information from just a small portion, small area, point measurement. Yeah, it's good. It's sensitive to chemicals and also rapid measurement, even non-destructive measurement. But because of point measurement, if the sample is many, like a seed, let's think about seed. There are 100 seeds, 1,000 seeds, even 100,000 seeds. If we want to measure each sample, individually, it takes a lot of time, right? So that's why spectral imaging is necessary for massive sample inspection. So spectral imaging consists of spectral information and spatial information. Okay, like this way. This is a small, let's assume this is a seed, that is small seed, but point by point measurement, it takes a lot of time. But if we can measure, these seed simultaneously, we can save a lot of time. Okay? That is, why spectral imaging is necessary. So spectral imaging is measure the spectral information for certain area. Sometimes it's wide. This is spectral imaging. The representative spectral imaging is hyperspectral images, right? Okay, hyperspectral image we call 3D hypercube because the information is 3D, right? X and Y spatial images plus spectral information. So that's why it's 3D hypercube, 3D information. Okay. Okay, when we measure this 3D information, how can we measure this 3D information? How can we construct, this 3D images? Okay, there are several methods. First, the simple method is point scanning. We can measure point by point and stack together to make 3D images. Another method is line scanning images. We can scan line by line to make 3D hypercube. And another method is area scanning. We just measure X and Y information at a certain wavelengths, and then using different wavelengths information, we can stack to make 3D hypercube. Okay, and the last one is the snapshot measurement. We can measure 3D information simultaneously. We can do that, but there is some limitation. I will talk about later. Okay, point measurement. We can measure one by one. It's very simple, but it takes a lot of time. Okay. Line scanning method, if we can illuminate line by line, and if we can measure line information, then it's a line by line to make 3D information. Okay. And area scanning, like this, okay, one by one at the different wavelengths to stack, to make 3D images. And this is, for example, this is a hyperspectral tunable filter microscope. So each wavelength shows different intensity. So by using, tunable filter, like area scanning, you can make hyperspectral images. That is also good. And the snapshot measurement, this is just a one-shot measurement, like this. This is an example of color images. Color images only 3 wavelengths, right? This is red and blue and also green. Okay? Green is 50%. The red is 25%. And blue is 25%. Then using that information, we can make a color images. Like this way. If we increase the wavelengths, we need optic, filter coating. This color image is only 3 wavelengths coating, right? Each pixels. But if we want to increase the wavelengths, we need more wavelengths coating, like this. Okay, here is 3 by 3 is 9. Okay. Okay. Sorry about this connection. Okay, I will continue. My presentation. Okay. So how to measure hyperspectral image using snapshot? Okay. So I already talked about RGB images, and also when we increase spectral wavelengths like this way. Okay, here 3 by 3. 1 pixel is 3 by 3 wavelengths. So total 9 wavelengths here. Okay, and here again, this is also 9 by 9, 3 by 3. So 9 wavelengths per pixel or so. So what I want to say is for snapshot measurement, the sensor should be designed special design. Okay, so if we increase spectral information, then the resolution gonna be down because the sensor size is limited. If we increase the wavelengths on the limited sensor size, the resolution should be reduced. Okay? That is a disadvantage of snapshot measurement, but it's convenient. Okay, line by line measurement. I prefer this methodologies. Why? Because it's easy to be implemented for online application, and also it is a high resolution with a fast measurement. So mostly agriculture and food materials line scanning method is preferred. Okay, there are several kinds of hyperspectral imaging. First one is hyperspectral reflectance images for visible range and NIR range. And also there is hyperspectral fluorescence images. It uses fluorescence. So mostly the range is visible range. And also there is hyperspectral Raman imagings. These images use Raman scattering. The Raman and infrared information is, complementary information. The polar molecular, structure, infrared sensitive, but unpolar molecular structures is Raman sensitive. So those are complementary information. So anyhow, today we're gonna focus on hyperspectral reflectance images. So maybe if I have chance, I will talk about fluorescence and Raman images later. In our laboratory, we have several kinds of hyperspectral imaging system: hyperspectral visible NIR measurement system, and hyperspectral fluorescence imaging system, and also hyperspectral short-wave infrared imaging system and hyperspectral Raman imaging system. So when we collect hyperspectral images, we need after collecting hyperspectral images, we need spectral analysis and make a model. Okay, so first, after collecting hyperspectral images, we need a background to remove. Okay, this is images, but we want to focus on only target material. Okay, background is not necessary. Okay, so we need to remove background information first, and then we can extract spectral information from our target area. Right? After that, we need spectral preprocessing. So I will talk about preprocessing in detail. But why we need the preprocessing? Because spectral measurement affected by environment, also the sample condition, etc. So we need to minimize the unwanted, influence. Okay? So that's why we need spectral preprocessing. Spectral preprocessing, there are many, methodology like normalization, derivative, etc. I will talk it, later. And then we need to develop model, two kinds of modeling: regression models and classification model. Regression model, for example, if we want to predict the sugar content or water content using a spectrum, we need a regression model. Okay? And regression model, there are several types of model: principal component regression, partial least square regression, and spot vector machine, and artificial neural network, etc. And classification. Classification is dividing groups. Okay, good or bad, two groups. Okay, maybe three groups. Low, medium, and high. So that is a grouping, right? That is a classification. Okay. So for classification, there are several models also: principal component analysis, partial least square discriminant analysis, and artificial neural network, convolution neural network, etc. So you can use your own model if you want. Okay, I want to talk about spectral preprocessing. Why spectral preprocessing is necessary? Because spectral measurement influenced by environment factors like temperature, humidity, even sample condition like surface roughness, sometimes affected by particle size. Okay, so it result in spectral variation. We call it scatter effect. Okay, this should be minimized. Why? Because we want to measure characteristics of materials, not environment, right? So we need to minimize environmental effect. This figure showed the scatter effect. So let's say there is a rough surface sample. Okay, when we illuminate the sample, the light reflectance, the reflection is very diverse. Some reflections, the path is very short. It gives high intensity. If the path is longer than shortest one, the intensity becomes less. Okay, so that effect result in the intensity difference of the spectrum like this. So if the sample surface is rough, the scatters become bigger. So that is an environmental effect. We need to minimize this effect. Okay, how to minimize the spectral scatter effect? So the simplest method is using normalization. Three kinds of normalization. So mean normalization. We can use mean value for the raw spectra is divided by mean value. So that is mean normalization. And raw spectrum divided by maximum values. This is a maximum normalization. And raw spectrum divided by certain range, so range normalization. So by this way, we can minimize the scatter effect. So that is an example. So raw data plot looks like this. There are some scatter effects. Okay, using mean normalization, we could minimize the scatter effect. Okay, so that is a example of spectral preprocessing. Another spectral preprocessing is multiplicative scatter correction. So that correction use reference spectrum. Okay, this equation. Sorry about the equation, but this equation here x okay x bar t is the mean of the data. So we want to use this data for reference. Okay, then okay, this data is raw data. Okay, then using this mean of the data, reference data, we can estimate the additive correction and multiplicative correction coefficients. We can we can calculate these two coefficients. Okay, using that coefficient, we can correct just measured spectrum like this way. Okay, this is additive correction and multiplicative correction. Then we can have reference like spectrum. So it is a corrected spectrum. Okay. Okay, another preprocessing is a standard normal variate. It's similar, but the additive corrections using mean of the variables and multiplicative corrections using standard deviation of the variables. So SMB provide auto-scaling effect. So the spectrum, the mean of the spectrum value becomes 0, and the standard of the spectrum become 1. Okay, so that is auto-scaling effect. So for if your sample is particle, SMB is very effective, okay, to minimize the sample variation. SMB is very good. And pre-processing, there are other pre-processing like derivative and statistical array, derivative. You can combine multiple pre-processing method. Okay, not only just using just one pre-processing, you can use multiple pre-processing if you want. Okay, when we measure hyperspectral images or spectral information, we need to extract spectral features, and we need spectral preprocessing, and also we need data labeling using ground truthing. Okay, when we measure sugar content measurement, we need to measure the sugar content of the material using refractometer, something like that, right? So that is ground truth values, Y values. Your X value is a spectral information, right? Then you have X values and Y values. Then you can make a model, okay? Regression model, classification model, whatever you want. Then you may need waveband selection. Why? Spectral information is huge. It's huge. Some information, some spectral information is not necessary for your analysis. Okay? You need to delete. You need to get rid of unuseful information. Okay? It increases the robustness of your model. Okay, so that's why we need a waveband selection. After making a model, then we can validate model using unused data. Okay, that is model validation or model test. So that is the whole process of spectral analysis. Okay, analysis method. Very simple method is just using combination of wavebands. Among the many spectral bands, you just choose 2 or 3 wavebands and make some equation. Okay. Division or subtract or additive. Okay. Very simple combination. Okay. So that is a simple waveband combination analysis. Okay. But that is some case, if the spectral information is very obvious, you can use a simple one. Okay? Simple is better, but if it is not enough, we need a comprehensive model, comprehensive analysis. There's a multivariate analysis or machine learning. The 2 types: regression and classification, as I told you earlier. In case of regression, there are 2 types also. Non-linear. So in case of a linear model, representative model is linear regression model, principal component regression model, partial least scale regression. So that is the linear model. Sport vector machine, random forest, and the classification model. Supervised model, supervised. Supervised model means we know spectral information to be create Y values, right? So if we Y value, it means ground truth, we can make supervised model, okay? Discriminant analysis and partial least scale discriminant analysis, or K nearest neighbor model or network, and that is supervised model. But if we don't know the Y value, sometimes we don't know the Y values, we cannot, analyze chemistry, or sometimes, okay, special case, we don't know the Y values, then we need to make a model using spectral information. So that is unsupervised model. So this model, principal component analysis, came. Okay, so those are some representative data method. Okay, when we collect hyperspectral images, we need noise removal and image correction. So this is because this is reflectance images, we need to calculate relative reflectance. This means if we measure white panel, it should be almost 100% reflectance, right? So using white references, we can adjust our reflectance value to relative reflectance values. Okay? And also dark current. Dark current means when we close the camera lens and measure the signal, that intensity, the sensor intensity is dark intensity, dark current. Okay, dark current is just a noise. We need to get rid of the. So that is and then we can extract. We can extract from our target materials, and then after preparing, we can make classification model or model, whatever we want. Okay. Then when we can apply model to a hyperspectral images. This way we can make chemical images. So that is our hyperspectral image analysis. Okay, I want to show some example of hyperspectral chemical composition measurement using hyperspectral reflectance images. When we, nutrition of food, that is, patty, hamburger patty, and chicken breast. Okay, so let's think about, the fat fat or the water distribution, in food. Okay, what our eyes like to burn hamburger patty or wear hamburger patty pretty well. The water content of hamburger patty, and we cannot, estimate the fat content of hamburger patty. It is not possible. We need some hyperspectral camera or spectral information with proper. So here, the hamburger patty we cut in the middle of hamburger patty. It looks delicious, but it's here. Okay, it's a reddish. Maybe and also Jewish. Looks Jewish. Maybe a more water content in the middle, and maybe some transparent particles. High fat. But we don't know exactly. We try to estimate, water content and fat content besides spectral information. Okay, using hyperspectral images, we can spectrally implement this area like chemistry. We choose values, right? Moisture content and fat content using chemistry. So using X values, spectral information, Y values, chemical, concentration chemistry, we can make a model, regression model. Okay? So that is the performance of the model. So looks like good. So using a model, we can construct chemical images using hyperspectral images. Okay, when we look at these figures, here is a fat concentration. So fat means higher fat contents. So when we look at some fat here, so it shows here also, right? Fat contribution and also water distribution. Mostly in the middle, so it's reasonable. The result is quite reasonable because water concentration, chemical imaging for images. Okay, let's move on. Another poultry inspection using hyperspectral reflection. Application is USDA, ARS. Okay. The regulation in the US, every poultry by human here over there. So look at the flying chicken. So the chicken move very fast. It's 3 to 5 chickens very fast. These guys look at glare at that chickens. There is some abnormal chickens. It's very tedious, right? It's very difficult to identify small abnormal area by human eyes, right? That's why USDA wanted to develop some automation inspection system. Okay, hyperspectral images, they investigate the wholesome or unwholesome chicken, and also they investigate the contamination on the surface of chicken. Because all slaughter process is automated. Okay, so the machine extract, digest the track automatically. Sometimes the tracks, cut, and some fecal matters overflow. Fecal matters comes out and contaminate the surface of chicken surface. Okay, so there is no good because there is a harmful, microbe inside the, fecal matters, right? So we need to identify and sort out the contaminated chickens. So using hyperspectral images, we can, make, classification model. So here, the systems, online systems using halogen lamp and hyperspectral images here. So it's a line by line scanning and apply the classification model and sort out the abnormal chickens. Okay, so this one is a video clip. The hyperspectral imaging system is a customized hyperspectral images. Okay, chicken breast, chicken, carcass, roof. The last two, chickens are diseased chicken. Okay. So everything is good. It's green light. Green light is, all good. If there is problems, it gives a red signal. The last two birds are diseased. Like this way. There are some disease, on chicken breast. So that is how hyperspectral imaging used. So again, close-up images. It's very difficult to identify the abnormal parts using naked eyes, but using hyperspectral images, you can identify the disease area correctly. And another one is fecal detection on surface of poultry. It's very similar. They are using only 3 wavelengths, selected wavelengths here. Only 3 wavelengths. Combination of 3 wavelengths, they can identify the fecal area. It's very simple, right? You don't need a comprehensive model, just a combination of 3 wavelengths. You can identify the, here, identify the contaminated surface. Sometimes life is easy. Sometimes life is very difficult. In this case, 2 things. First one is a complicated one. Second one is easier one. So power window will show the contaminants in chicken surface. Here, there's some fecal matter contamination. Close-up images like this, no contamination, and some contaminated area pops up to 1 like this way. Okay, this is an example. And another example is seed sorting using hyperspectral reflectance images. It's done by my laboratory. So we're gonna inspect seed viability, live seed and dead seed. We try to classify the viability using hyperspectral images. After hyperspectral imaging, measurement, we germinate the seed, to make ground truth values. If the seed is, germinated, this is good groups. Not germinated is no good groups. Only 2 groups. Okay, so using these 2 Y values, you can make classification model. So for online inspection system, we make this prototype. Automated seed, conveyor belt, and also hyperspectral images, light source, and also minus pressure sorting system. If the seed is no good, we just suck out. Okay, so that is our online inspection system. Okay, so here, watermelon seed, the seedless watermelon seed. Seedless watermelon seed is very expensive in Korea. And also tomato seed, paprika seed is very expensive. It's like a gold. It's like gold. Okay. So line by scanning, we measure the seed, the hyperspectral images of seed, and then apply already developed classification model, and we can identify which seed is good, which is no good. If the seed is no good, we suck out the seed like this way, suck out and throw it away like this way. So if the seed is good, it passes through the conveyor belt and collected in a basket like this. This way, we can, divide good seed, bad seed. That is a prototype of seed inspection system. Okay, another one is a real-time soybean sorting system. Okay, this is faster because the soybeans, we have to measure one by one soybean seed. Okay? There are tons of soybean seed. How can we measure? We need a very fast measurement system. So using a fast hyperspectral imaging system, we classify the soybean seed based on protein content. Because the soybean seed is a very useful protein source, right? Some soybean seed low protein, some soybean seed high protein. So using the protein-based soybean sorting, we can improve the quality of soy. So here, protein-based model is three classifications: so low protein, the middle protein, and the high protein. So using that model, we classify soybean seed. So while the soybean is dropped, okay, and then very fast hyperspectral images, and then we classify the soybean seed using compressed air. We just shoot the soybean to classify the soybeans based on protein content. That is a real-time soybean sorting system. Nowadays, hyperspectral imaging technology is very advanced, and we can use very fast hyperspectral images. Okay, another application is spectral imaging based plant stress measurement. So abiotic stress and biotic stress. Okay, still we are using visible NIR, fluorescence, and infrared hyperspectral images. Here, watermelon hyperspectral images. We just remove the background using just the deep learning measurement. Okay. Everybody using deep learning, right? So we just use deep learning for remove the background, simple, and then extract spectral information from the seed. Not seed, from the plant. Then the plant is exposed to drought stress. After some time, we stop the watering and then measure the leaves, the stressed leaves every 2 days. Here, like this. Okay, hyperspectral images result. Okay, control plant means no stressed plant. Okay, every 2 years, every 2 days, 2 days, 4 days, after 6 days, 8 days, 10 days, 12 days, 14 days. There is some, differences, right? By using that way, we can identify the stressed plants. Another one is a biochemical phenotyping. We wanted to predict phenolic compound and flavonoid compounds using hyperspectral images. Using wet chemistry, we can make estimation, quantitative analysis model like a PLSR model, and then apply this model to hyperspectral images. The interesting things is here, this is a phenolic compound. The first row is a control. The control plant almost, same. There is no change, based on time. This is, sorry about, there is the number is missed, okay? This is a 0, 2 days, 4 days, 6 days, 8 days, 10 days, and 12 days, something like that. So there is no change control. But without stress, okay, there is no change, but after 10 days, the phenolic compound, suddenly increased. There is a very interesting, finding. So certain days, it increased rapidly. And the flavonoid control plant, there is almost the same, but throughout the stress, okay, after 10 days, the flavonoid increased suddenly. That is a very interesting finding also. Okay. So using that technology, we can estimate the optimal harvesting time if we want to maximize some useful chemical composition. Okay, so using hyperspectral images, we can estimate optimal harvesting time. Okay, and the antioxidant activities, we try to estimate the 3 types of antioxidant activities. So it's similar, very similar. There's 3 types of antioxidant, and the control is about the same. But drought-stressed plant, similarly, after 10 days, the antioxidant contents concentration suddenly increases. So that is also indicate the optimal harvesting time or the quality control of the plants. Okay, another example, deep learning-based hyperspectral image analysis. This is for spacecraft. This craft is developed by NASA, Kennedy Space Center. They developed this, dragon letters for astronauts in International Space Station. Okay, before using that, letters, they wanted to make some model to identify stressed or not stressed, letters. So we are collaborating with NASA, and they raised the letters, and USGARS and our team measured hyperspectral images, and also we make artificial intelligence model. And using explainable artificial intelligence model, the result is like that. So first row is control, so no stress, and the second one is the stress. So the red color means stress index. Okay? Using explainable AI, when we look at the stressed one, the darker the red color is edge of plant. Okay? It means the stress initiated, through the edge of the plants. So that is very interesting one. And also we can identify the stressed letters after 3 days. Before 3 days, exactly same, but after 3 days, after stopping the water, and then 3 days passed, we can identify which one is stressed, which one is not stressed. So that is an example of drought stress diagnosis. And lastly, as a deep multimodal fusion network for high throughput phenotyping, the title is very complicated. It means we combine several types of imaging technique together. Okay? So here, RGB images and the hyperspectral near infrared images, and also multispectral fluorescence images and the thermal images together to monitor the plant. Okay, this is a video clip of the system. Automatically, the plants comes in and out. So this first one is RGB images. Second one is hyperspectral NIR images. There is some moving, light here, right? Hyperspectral imaging line scanning system. After that, you move to another chamber for multispectral fluorescence images. This is a this is a violet, the light, to measure fluorescence. And then after that, move to another chamber for thermal imaging. Okay, so automatically measurement. So 4 different types of imaging technique together, we can make multimodal fusion network. So here, RGB images, thermal image, just 2D images. We can use quite simple deep learning model, and hyperspectral images and multispectral images is 3D information. Then is complicated model. So everything together to monitor the stressed one or disease one classification model. The performance looks pretty nice. All right, and how to use the system? Okay, hyperspectral image is expensive and bulky sometimes. We try to use the system in the field, practical use. That is what we are doing now. Okay, so this is a hyperspectral imaging system for strawberry stress measurement in greenhouse. The research is going on, and hyperspectral imaging system for potato drought stress measurement. And sometimes we are using drone hyperspectral images and drone multispectral images to predict, stress of plant or predict the fertilization in plant field. This is an example of prediction of fertilization in garlic field. So that's what we are doing now. Okay, this is a closing remark. The demands for high quality and safety food and agricultural material increases. So we need accurate, objective, digital measurement technique, and that technique will be more popular in the future. And non-destructive measurement, hyperspectral, multispectral imaging will be much more popular in the future, and the price and the measurement speed is going, to be improved now. And my concern is how to make cost-effective and field-deployable system development for real-time and on-site application. That is what I'm concerned now. So we need to use hyperspectral imaging system in real fields. That is what I'm doing now. And AI, deep learning model, it is very popular now. It's AI model, everybody using deep learning model. So there is a good chance we can use it, to improve the performance of our, analysis model, right? It gives synergetic effect with the spectral imaging or spectral analysis also. But we have to be careful. Should not be overfitted, right? Overfitted. Should not be overfitted. So that is very important. So spectral information, efficient and robust analysis technique. We still need efficient and robust analysis technique. And also spatial informations, we can implement AI deep learning model to improve the model performance. All right, so that's all for today's talk. If you have any questions, please let me know.
Thank you, Prof. Cho. for your presentation. Some of students here are doing their research in using visible near infrared but point spectroscopy. And maybe you have questions about your research. Maybe you want to discuss with Prof. Cho to, for example, you're not you haven't done with your research or your experiment, but you want to make sure that your spectra will be good, yeah, because the spectra is important. Maybe if you want to ask, or maybe you can ask anything with Prof. Cho. I think the time is very good, yeah, now, yeah. We're very grateful to have Prof. Cho here. Okay, any questions from students here in the room? Yeah, okay, please.
So, the hyperspectral imaging and spectroscopy actually really affected by environment condition. But I want to know, in Indonesia we have only 2 seasons, and the temperature actually not really high or low. Not like maybe in Korea, there are 4 seasons like winter and summer, which has very different condition with humidity and temperature. So when we have those conditions in environment, how we do the measurement with using this device.
Okay. As you told me, the temperature is more stable in Indonesia, much better than Korea. But when you measure hyperspectral images, you always have to calibrate your images using reflectance pattern. Okay. Regardless of the temperature condition, you have to calibrate your system. Like a white panel, we assume it's 100% in reflectance, and sometimes 30% reflectance material, sometimes 60% reflectance panels also. For in my case, hyperspectral imaging, drone hyperspectral imaging measurement, we are using 3 types of different reflectance panels: 30, 60, and 90. This way, we calibrate our system. Always, it doesn't matter, how the temperature it is. Whenever you measure, you need to calibrate the system. And also, the important thing is, I also, mentioned this one in Andreas, examination, and the stability of your system is very important. When you use a light source, the light source intensity should be stabilized. Sometimes you need to wait 1 hour to stabilize your light source. And sometimes you need to 10 minutes or 15 minutes to stabilize your sensor. You need to check, this your system calibration and stabilization. That is very important. Otherwise, the measurement keep changing. Even though you have very good, model, the performance is not good. It is very important. Okay, thanks for the question.
And do you think that the environment always means temperature and humidity, or what do you mean by environment? It should be not only that.
Right. Environment change, let's say it's spectroscopic, measurement. If the room temperature is changing, it affects the sensor performance. Okay. So, if the measurement takes 1 minute, let's say 1 minute, the measurement start short wavelengths, okay, short wavelengths, and then move to a longer wavelengths measurement. While then measurement, the temperature change. Okay, the sensor response will be changing, and your spectrum will be skewed. Your spectrum, the slope of your spectrum become, changes. That is the environment effect. And how can we collect, this one? So if you have a reference in a spectrum, using that reference spectrum, you can calibrate, you can correct your spectrum using SNV model or MSC model, because you have reference. Okay? Using that way, you can, correct, additive, coefficients, additive effect, and multiplicative. Multiplicative means slope. You can, correct that effect. That is important. So we don't know, the environment effect. So the safest way is just to use pre-processing method. That is the safest way.
And do the calibration more often?
More often, that is also helpful. Helpful.
Sometimes we save the reference in the system, and then sometimes we just calibrate using that system, not do the reference one in the real, what I mean here. Sometimes we record the white reference and then we put in the system, and then we do it.
Yeah, that's also possible.
Possible.
Yes, that's also
we don't
possible.
Have to measure many times for the white reference.
No, I mean the shape of your white reference spectrum is okay, but if the environment is changing, like the temperature changing, we need to measure again, because the intensity may be different, right? So I recommend frequent calibration.
Frequent calibration. Intan, I think she's measuring the spectra now, and Prof. Cho gave a good recommendation that sometimes we have to wait, check the white reference, whether the intensity is stable during 1 hour, for example, and you measure several times and see whether it's at the same intensity or not.
So I recommend just to turn on the spectrometer, and just to wait 1 hour, and then measure and start to measure the intensity while turn on the light source.
First, only spectrometer turn on for 1 hour
for the stabilized test of light source.
Yeah.
Then the intensity of spectrum is keep changing, keep increasing. Depends on the light source, stability.
Okay.
At a certain time, the signal is stabilized. That time is your light source stabilized time, right? Maybe it will take 40 minutes or 1 hour. We don't know. You have to check. You have to check. So that is your light source stabilized time. Vice versa. And then if when the stabilized time of your light source, then now everything turn off, and then turn on your light source, and just wait until the stabilized time, and then turn on your spectrometer, then check the intensity. In a certain period, the intensity is stabilized. That is your sensor stabilized time. Okay? You have to check both.
Both the sensor and
the light source. That is very important. Otherwise, your old data is, I think, no good. It's not convincing.
Sometimes because we heard that you cannot turn off the light when you start measuring this. Otherwise, it will take time to heat it up again.
Yes.
So you mean that 1 hour is
mostly 1 hour is enough, but you need to check.
yeah.
You need to check.
Other questions?
It's got the distance between the probe and the
What
object.
about the distance
It's a-
between the probe
probe
and the samples? Do you have a idea?
It doesn't matter.
Doesn't matter.
It's about the intensity of your spectrum. The maximum intensity of your spectrum should not be saturated, right? If there is a sensor saturation values, the maximum value of your spectrum should be 70%. 70% of the maximum value. Usually, is avoid them. That's why you can avoid saturation.
Avoid saturation.
Saturation.
Too many light.
Yeah,
Too many lights.
And what about the background you want to ask? Because our sensor maybe need this diameter and the sample is too small, and then maybe for vanilla also, yeah. If the surface of the probe is too big, bigger than the samples, and then do you recommend or how to? We are not sure whether, because it's reflectance, right? Reflectance, and then the background will reflect that. You have idea of what background do we have to use? White or black or?
Your sensor is too big.
2 centimeters, for example,
2
for diameter, yeah.
Centimeter.
And the seed maybe only
Sheet
one.
is very small.
Yeah, very small. If you measure one seed.
Yeah, so you can you can decrease the distance, maybe, or you can block. You can block.
Black.
Block
the outside
of the sensor.
Okay.
That is another way, because we don't want to unwanted signal.
Yeah.
We can color. I mean the blogger with can color.
Black will be black.
And also the background of the samples.
Black would be fine. Black would be fine because it minimize reflectance. It's very fine.
Mana pakai black ya?
Saya nanti ke depan back.
Yeah. Oh yeah, there's one question in the Zoom. Okay, let me check. Which filter pattern is used to speed up the scanning process?
Which
filter pattern?
Filter pattern. What kind of filter? Filter pattern?
Maksudnya apa mungkin, atau bisa bertanya langsung? Ini Mas Angga ya? Angga Devian apa? Mas Angga ya? Mas Angga mau tanya langsung? What do you mean by filter pattern? Mas Angga? Are you there?
Maybe.
Oh yeah. Okay.
There's another beberapa pattern kan. Ada mozaik, kemudian ada apa itu ya? Lupa saya. Ada tiga pattern pembacaan scan-nya itu. Ada mozaik sama apa tadi ya?
Snapshot, line, bukan? Which one?
Yep. Tunggu sebentar, Bu. Lupa pula benarnya.
Let me guess. Hyperspectral. There is a filter. Snapshot. Okay, this one.
Oh, this one, tile and line.
Yeah.
This one,
Yeah.
mosaic pattern or tile or line.
Mosaic pattern would be the best. Because tiled pattern, the line patterns, because so one specific waveband is some area, so it affected by spatial information, but mosaic pattern. So every spectrum is just small certain region and distributed evenly. So I mostly snapshot hyperspectral imagers is a mosaic pattern. But sometimes you can use a tidal pattern, line pattern, but mostly mosaic pattern to be better.
So the resolution.
Okay.
Yeah, resolution is the same. The resolution is the same. But this snapshot measurement resolution is lower than other measurement method. That is a limitation of snapshot method.
Okay, does it answer your question, Mas?
Yeah, thank you.
Okay, thank you. There is another question from Reza. Hey, Reza, please. You can ask directly to Prof. Cho.
All right. Is it audible, my voice?
Yes, clear.
Okay, first of all, good afternoon, Professor Chu and another professors there. My name is Reza. I was Professor Hanim and Professor Effie students, but right now I am in Professor Hunsuli's laboratory.
Sorry.
And
Student.
yes, I am Professor Hunsuli's student.
Okay, please.
So it is interesting when you are discussing about the time series measurement. As in our lab recently, we're working on some kind of measurement that in the time sequences, something like that. And what is interesting to me is there any algorithm or is that worth to apply some compensation? I mean, some algorithms like a calibration transfer or something that can compensate the effect of the different day measurement as to when we want to measure the samples like plant stress or something that usually we measure every single day during a certain period. Is that worth or is there any technique that can compensate this different measurement? Thank you.
Oh, okay. Let me introduce. Let me explain myself. Your question. You are measuring time dependent measurement, right? And then also which time is best for the measurement in a day, maybe. So anyhow, okay, it doesn't matter. Okay, so even though you are doing time dependent measurement, we have to calibrate the system always. Okay? If you even though the daytime, nighttime, it's different. But when you are using the light source, okay, you can still measure your target consistently by calibrating the system. Okay? So whenever you measure at a certain time in the day, you have to check, the calibration of your system. So that is very important.
Is it answer your question?
Is that answer your question?
Yes, already. Thank you, Professor.
Okay. Another question from this group?
No, go ahead.
Thank you, Professor. Nice to see you again after 3 years. Actually, nowadays the research trend is deep learning and AI. However, at the time, the soybean seeds that I use is only 200 until 300. So what if I want to make it like deep learning, but the data only only limited. Well, maybe the solution is using the powder data. However, what about the seed data? If I want to make it like deep learning.
Yeah, mostly for deep learning model, I recommend 1,000
Right.
data size. That is a rule of thumb in deep learning analysis, mostly. Okay. So if you have a less amount of sample size, then mostly we have to, worrying about, overfitting problem. Your sample should be, enough. The number should be enough to avoid overfitting.
So I should take more.
More. Yeah.
More.
So deep learning, I like deep learning model, but in this case, if the linear model is not working, then maybe we can use deep learning model. Okay. If your case, linear model is good enough, no need to use deep learning. Why? Because the linear model is a robust model. Okay. That's enough. Okay. Why you make your life complicated? Right? Don't use deep learning as long as your
Maybe for the
linear model is good enough.
For the novel.
For publication.
Yeah, publication. Yeah, but always I facing this kind of question. Okay, so when we provide linear model and non-linear model, deep learning model, everything together, but linear model is still good enough. Why other model is necessary? There is no. It's not novelty.
All right.
Because non-linear model is already established, and deep learning model is transfer learning, right? We didn't develop the deep learning model itself. We just use, and then we just modify the end parts. That is not a novelty. So focus on good model, even though it is a linear model, it's a value.
It's the old way.
So we need to think about differently. Okay, so novelty is not putting everything together. That is not novelty. Okay? Even though when you use a linear model, think about creativity. Okay, that is a novelty. Okay, so yeah, that's important.
Yeah. Okay, Prof. Okay, Prof. There is one question from Mr. Slamet Widodo. He's a lecturer from the Institut Pertanian Bogor. So it's from other university. Okay, Pak Slamet, silakan.
Okay, thank you, Dr. Evi. Good afternoon, Professor Cho. Yes, my name is, please let me introduce myself. My name is Slamet Widodo. You can call me Slamet or Widodo. So I'm from Bogor Agricultural University. And thank you very much for your very interesting presentation. And also, Dr. Evi, thank you for inviting me to this webinar. So currently we have some project with Dr. Evi for some quality assessment for the vanilla. But my question is not related to the vanilla actually. So I have some question about I think like me or maybe Dr. Evi, I think working with some spectroscopy method for quality assessment and so on. And of course, we want to bring our research not only in our laboratory, right? So, and also this is really that we want to have some impact to our society. So I want to know about your experience, Professor Cho, about how actually we can bring our research, because usually in the laboratory it's just some proven concept or maybe some theoretical work, but how actually we can bring it in the real application, and or how to bring it some collaborative work with some industry to make it more applicable in the real application. Maybe you have some experience maybe in your laboratory in Korea. So how actually we can do this research to be more impactful to the society, and then you can bring it to the some commercial stage. Thank you very much.
Thank you for the good question. In my case, we are applying hyperspectral images for post-harvesting industry. already multispectral and hyperspectral imaging technique is using post-harvest industry. After harvesting the fruits and vegetables, we can, assure the quality and safety of the material. That is a very practical application. But pre-harvest, research is still, in a research stage. So that's why we are, we are concerned about. We are, trying to develop field deployable, technique for pre-harvest. I mean, like plant stress monitoring and fertilization, monitoring. So this kind of research is still on the way, in the middle of research stage. But post-harvest area is becomes very practical now. So if you apply this spectroscopic techniques for vanilla quality measurement, why don't you use for post-harvest area? I mean, you can assure the quality, chemical composition of vanilla, for company. So that would be a good application, I think. Is that your is the answer for your question, or you wanna ask another?
Yes. So actually, I think the situation like in Indonesia and Korea a little bit different, right? Because in Korea, maybe the consumer is a little bit more educated. They concerned about the quality. They want to pay more for the higher quality product, but maybe a little bit different with Indonesia. And also in terms of the instrument, like the sensors, I think in the Korea you can find a lot of sensors, and also in Indonesia, I think it's quite difficult. We still depend on some imported part. For example, we can import some sensor maybe from Korea or Japan or other country. So I think this is a limitation in Indonesia. So that's why we are always thinking about how to make it more affordable. So one way that I think it might be applicable in say we working with some little bit low cost, for example, like a portable spectrometer, for example, because it is a little bit cheaper, right, Professor Cho? But the problem is like of course the resolution is low, and also of course the stability and so on. I think the quality will be different. So what do you think? Which approach actually will be applicable if you want to bring this spectroscopy technique to Indonesian market? I think. Second, what I want to know. What is your opinion? I think.
Right. Yeah. I think the application area better than me in Indonesia, but low cost system is very important also. Okay, you can use a spectrometer for screening. If you can find the screening problem, not just delicate chemical concentration prediction. Instead of that delicate estimation, you can find screening problems, good or bad, or something like that, right? The screening problem is much easier to approach. Finding application is very important. Okay, identify your problem, and then you can use even low resolution equipment is good enough sometimes, right? So try to find good application. I think that is very important.
Okay, thank you, Professor Cho.
Thank you.
Thank you, Osama. Another question? Maybe one question. Okay, I have one question, Prof. I was thinking that can we use? I know we can, but maybe you think that it's not efficient. Or, for example, if I want to make a chemical map using point spectroscopy, it means that I have to take the spectra in many points. Do you think is it possible, or just plus?
Yes, it's possible, but the problem it takes time.
Yeah.
If time doesn't matter, Yeah, it's okay.
Mm.
Previously, point measurement was, common method before line scanning, before hyperspectral imaging technologies. Just point measurement and to make, chemical images also useful. You can use it. Yes.
So what methods do you think?
You need a XY, a control system, right? XY positioning system. And mostly in that case, your sample should be flat, right? So if you met, this condition, you can use XY, point measurement to make, chemical images. Yes, also it's possible.
But the outcomes is not as good as light skin.
No. I think it should be same.
So
Yes.
depends
It
on
depends on resolution.
Yeah.
If you control XY resolution, you can do whatever. It's a time matter. It's a time matter.
Okay. Thank you,
Yes.
Prof. Any other question? Mariana? No? Paluki? No? Ozzy? Okay. I think because we have come to the end of the presentation, Prof. Cho, I think it's a very good opportunity for us to have a lecture from you, and it's one maybe we will do this again, maybe Prof. Cho in the future. So for today, we give applause to.
Thank you very much.
Thank you very much, Prof. Cho. And I think we can end this session. Thank you very much. Okay, good afternoon.
Okay. Good afternoon.